Okay, so in the last part of our module, we're going to take a look at two things. We're going to take a look at some of the shapes that covalent compounds can have. And we're also going to talk about polarity, a little bit about polarity of covalent compounds. And we just sort of finished talking about polarity of bonds in our discussion of electronegativity. The next sort of step of that is to talk about polarity of compounds. In this video, we'll talk about shape. And then in the last video for the module, we'll take a look at polarity, some aspects of polarity of covalent compounds. All right, so let's talk a little bit about shape. Essentially, shape is predicted by using what is known as Vesper theory. Vesper stands for valence shell electron pair repulsion, which they are nice enough to abbreviate as Vesper. So we often call it Vesper theory. Essentially, the trademark of Vesper theory is that it states that the shape around an atom is determined by the number of bonds and lone pairs of electrons attached to that atom. Okay. Now, most of the time when you use Vesper theory, you talk about what essentially is, or when you predict shape, usually it's around a central atom. So just to show you like an example, if you had something like methane, CH4, which we saw a little bit about earlier in the module, the shape of CH4, as we'll talk about in a few moments, is actually based on the shape around the carbon, because the carbon here would be the central atom. Usually we don't apply Vesper theory to things that are sort of on the ends of a compound. And usually for those aspects, you have things that are sort of in the middle, which we can predict the shape around, or you have things on an end. Just to show you another example, if you go on and take organic, you're going to talk about a compound known as ethane. For ethane, where you have 2 carbons and 6 hydrogens, both of the carbons are considered central atoms. So in fact, you can predict the shape around each of those central atoms, okay? So essentially, Vesper, and for this course, essentially, we're looking at compounds that have a single central atom, but basically you could have compounds that have multiple central atoms, especially in the world of organic. That's very, very much possible, okay? So basically it determines the shape around an atom by the number of bonds and lone pairs of electrons attached to, let's just do a little bit of correction here, attached to that atom. Now, the shapes are predicated on having the electron groups, which are bonds and lone pairs of electrons, arranged as far apart as possible around the atom. To minimize what? Well, to minimize repulsion. Because if you think about opposite charges, we know that opposite charges attract. But what do we know about like charges? Like charges do what? Like charges repel. So you have bonds that contain electrons. You have lone pairs that contain electrons. Well, electrons have negative charges. So if they get too close to each other, that's going to be a repulsive force. So that's what the shapes are sort of predicated on. They're predicated on having the bonds and lone pairs arranged as far apart as possible to minimize possible repulsions. Okay. So we can have a very, very long discussion on Vesper theory. But what we're really going to focus on are the 3 examples where you have a central atom with 4 electron groups. Different combinations of bonds and lone pairs to give us essentially 8 electrons total around the central atom. 4 electron groups, essentially with 2 electrons per group, would give us 8 electrons total. That's the focus on here. In the first example, we take a look at CH4, all right? So it turns out that for CH4, there are 4 single bonds and no lone pairs of electrons around the central atom. And we did this work. We said, okay, if you take the carbon with 4 valence electrons and put hydrogens around it with 1 valence electron each, in order for everything to satisfy the octet rule, that carbon is going to form single bonds with each of the hydrogens. Now, when we draw it, and I know I didn't do it perfectly here, but when we draw it, we usually draw it with the hydrogens off the carbon going straight up, straight down, straight to the left, and straight to the right. In reality, if you were to look at the actual structure of CH4, would CH4 have that shape with the carbon in the middle and the hydrogens going straight up, straight down, straight to the left, and straight to the right? And the answer is no. It turns out that repulsion is minimized by placing the four groups, in this case, the four single bonds, at the corners of a tetrahedron with bond angles of 109 degrees. So the shape around an atom, when that atom has four single bonds and no lone pairs of electrons, what Vesper theory says is that if you have an atom, a central atom, with four single bonds and no lone pairs of electrons, the shape around that atom is going to be tetrahedral. And what does something tetrahedral look like? Well, on the bottom here, you have sort of a model of what methane CH4 would look like, with the carbon in the middle and the hydrogens attached to it. And if you notice, do the hydrogens go straight up, straight down, straight to the left, and straight to the right? The answer is no. Essentially, the hydrogens are positioned towards the corners of a tetrahedron. So what you have here is a tetrahedral shape. So four single bonds, no lone pairs of electrons. The shape around that atom is going to be tetrahedral. Okay. In our next example, we come across ammonia, Nh3. So let's do a little bit of work on this first. So nitrogen, 5 valence electrons. The goal is to get to 8. Each hydrogen with 1 valence electron. The goal is to get to 2. Okay. So what's going to go on here for everything to satisfy the octet rule? Well, each hydrogen, it's going to share. Sorry, I got to put another electron on that nitrogen. Each hydrogen is going to share one of its valence electrons, or its 1 valence electron with nitrogen. And the nitrogen has valence electrons itself to share back, forming what types of bonds between those hydrogens and the nitrogen? Forming single bonds, because they're going to be sharing 2 electrons total. And that goes for the hydrogen on the left, the hydrogen on the top, and the hydrogen on the right. And the nitrogen still has a pair of electrons, a lone pair of electrons, that it's not used in chemical bonding. So each hydrogen is happy because each hydrogen now has 2 valence electrons. And the nitrogen is happy because the nitrogen now has 2, 4, 6, 8 valence electrons. So the octet rule is satisfied. So as you see here, in a molecule of NH3, remember covalent compounds are made up of molecules of that compound. There are 3 single bonds and a lone pair of electrons around the central atom, the nitrogen. The question now becomes, what does Vesper theory say about the shape around an atom when that atom has 3 single bonds and a lone pair of electrons? Do the hydrogens here, the way I've drawn it, go straight to the left, straight to the right, or straight up and straight up? Does it look like that? And the answer is no. It turns out that, according to Vesper theory, when an atom has 3 single bonds and a lone pair of electrons, the shape around that atom is trigonal pyramidal. And on the slide here, on the screen, you have what ammonia Nh3 with the trigonal pyramidal shape looks like. And if you notice the way they have it, you have a bond coming towards you. You have a bond going sort of away from you, going to the left, and you have a bond going away from you, sort of going to the right. That's essentially the arrangement of a trigonal pyramidal shape. Where essentially would the lone pair of electrons be? Essentially, the lone pair of electrons would be at the top. That's present. Okay. So, and this is another way of having 4 electron groups in a sense, because in methane, the 4 electron groups were 4 single bonds. Here, the 4 groups are the 3 single bonds and the lone pair. That's the 4 electron groups in this example. Okay. One more. Water. Okay. So again, let's do a little bit of work. Here's our hydrogen. Here's our oxygen. We know for oxygen, oxygen has 6 valence electrons. The goal is to get to 8. Each hydrogen has 1 valence electron. The goal is to get to 2. So in order for everything to be happy, each hydrogen is going to share its 1 electron with the oxygen. And the oxygen has valence electrons to respond in kind. So between those hydrogens and the oxygen, what are you going to have between them? You're going to have single bonds. And the oxygen carries with it 2 lone pairs of electrons, 2 pairs of electrons that are not involved in chemical bonding. So this oxygen now has 2, 4, 6, 8 valence electrons, and the hydrogens are happy here too. So in a molecule of water, again, covalent compounds are made up of molecules of that compound. There are 2 single bonds and 2 lone pairs around the central atom oxygen. So now the question becomes, what does Vesper theory state when an atom has 2 single bonds and 2 lone pairs around it? Well, according to Vesper theory, the shape around an atom when it has 2 single bonds and 2 lone pairs is the shape around that atom is bent. What does water look like? What does something bent look like? It looks like right here. Essentially what it looks like, if you were sort of looking at it from a different angle, it looks essentially like an upside down V. The main point is that in water, the H, the O, and the H don't go straight across. It's not a shape. It's not linear. If it was straight across, it would be linear. This is a bent shape. And essentially, where would the lone pairs be? Essentially, the lone pairs would be there on the atom. All right? But you have a bent shape, sort of looking like an upside down V associated with it. So when an atom, according to Vesper theory, when an atom has 2 single bonds and 2 lone pairs, which again, if you add those up, that would be the 4 electron group, the 2 single bonds and the 2 lone pairs. When an atom has 2 single bonds and 2 lone pairs, the shape around that atom is bent. Okay. And for this course, those are the 3 shapes I expect you to be able to recognize. Because as I said, we could have a much longer discussion of shape, linear, trigonal planar. We could talk about octahedral, seesaw even. There's a shape called the seesaw. But for our course, we limit it to these 3. All right. So let's look at an example. Predict the shape of H2s. All right. How would we do it? Well, the first thing we want to do is we want to take a look at an electron dot or a Lewis dot structure. Because essentially, to predict the shape, we need to know what's going around. We need to know what's going on around the sulfur in terms of bonds and lone pairs of electrons. So the only way to do that essentially is to draw the electron dot structure of it. So for hydrogen, we know it has 1 valence electron. The goal is to get to 2. Just like oxygen, sulfur has 6 valence electrons. The goal is to get to 8. So to have the octet rules satisfied, the sulfur is going to form a single bond to each of the hydrogens. Each hydrogen will share its 1 valence electron with sulfur, and the sulfur will respond in kind by sharing a valence electron with each of those hydrogens to form single bonds between them. And that works out very well because when that happens, the sulfur now has 2, 4, 6, 8 valence electrons. And of course, the hydrogen has 2 valence electrons as well. So now, once we have this electron dot structure, we can see what's going on around the sulfur, the central atom here, and predict the shape. So around the sulfur, what do we have? We have 2 single bonds and 2 lone pairs of electrons. Right? 2 single bonds, 2 lone pairs of electrons. So according to Vesper theory, what shape do you have around an atom when that atom has 2 bonds and 2 lone pairs of electrons? The shape around that atom is bent. So the shape of H2s would be said to be